All right. Hello, everyone. Welcome back to Physical Geology 1403. How we doing? We're doing. That's what I like to hear. Today is lecture 13, the last lecture. We are diving a little deeper into crustal deformation and mountains. That's how we're going to wrap up the semester, just kind of bringing it all home, so to speak. But before we jump into that, as usual, I want to offer the opportunity for y'all to ask any questions you may have. It is finals week here at OC. So today you're getting your last lecture. The next time we meet will be the final exam review. And then that's it, aside from all of you who see me the next week for 1404. Oh, the despair. Yeah, the victory.
Wait, there's talking next week?
Yeah. Yeah.
There's no break between the 8 weeks like there was last year?
I believe 1404 is Monday, Wednesday, and we start on Wednesday next week. So depending on when your classes are, I believe the semester starts on Tuesday. So depending on when your classes are, you could have your first day of class on Wednesday or on Tuesday.
That's fine.
Yeah. I don't even get Monday if it makes you feel better. I submit final grades for this semester on Friday, and then I'm back on Monday to prepare for fall 2.
Yeah.
Nice monocle.
Yeah.
For those of you that are taking 1404 from me next semester, by the way, Halloween does fall in that term. And even though Halloween's on a Thursday, I will be coming in full costume on the 30th to teach. That's kind of a tradition of mine. If any of you want to join me in costume, please feel free. What am I going to dress as? Oh, you'll just have to wait and see, won't ya?
You'll be a good Indiana Jones.
Wouldn't be much of a costume. I literally have all of the right stuff in my office. Okay, let's see what else. If you have not taken exams, do it today or tomorrow at the latest. Today, I am going in and I'm doing my last pre-final run through of everything that's been turned in. And anything that hasn't been turned in gets a 0 on it. You can still get full credit on it, but that's gonna wait until I go and I regrade everything when I do finals. Okay, so between now and the day that I submit final grades, anything that hasn't been turned in will have a 0 on it until I go and see it on finals submission day. Okay, so just bear that in mind. Unless you're extra super duper confident that you can get everything turned in, now is the time. Okay. We had our class movie night last week. It was fun. Thank you everyone who came to that. We had a good time. I think we had 16 people there between the 3 classes that I teach. There was some family. Some people brought friends. It was awesome. My son is adorable. Thank you so much for that. Thank you for being so kind to him. Both of you. It was good.
You brought the grill?
Huh?
The grill?
The drill? The grill? Oh yeah, no, I was in there flipping patties. No. Some things you're just not allowed to do inside. The grill outside? I'll have to have an outdoors movie night. There'll be a lot more involved in that. This class and that classroom, this is my kingdom. No one bothers me about what I do in here. Within constraints. I can't start a fire and have a grill, right? Nobody cares what else I do as long as it doesn't endanger safety. But if I try doing anything in any other room or any other facility on campus, I have to file paperwork, and I don't like paperwork. So, okay. All right, questions, comments? Any songs, dances, jokes? No? Yes? Yeah, 1404 does have an extra credit movie day as well. Except that one's focused more along the lines of not movies that make fun of geology, movies that make fun of the science that we discussed. So like dinosaurs or not movies that make fun of it so much as, like with 2012 was movies that try and incorporate that science, but sometimes come off ridiculous. Yeah. So we'll talk about like Jurassic Park. We'll talk about like Ice Age will be an option. There are a couple of other things. Some asteroid movies, Greenland, because we talked about asteroids for a while. We don't really know. The Good Dinosaur isn't really an option. That movie knows what it is, right? That movie knows what it is. Huh? Say that again.
Have your son watch it with us, you know?
Oh, he will. No, he'll come and watch. He'll come and watch those too. He loves those movies. Yeah. Although I did realize, for those of you who were there at the movie night this last week, he's been totally cool with all these movies. But last night, or not last night, at that movie night, he was getting a little freaked out about some parts. And I realized maybe before he wasn't old enough to know he should be scared. And now he is old enough to start realizing this is something that should scare me. And that's why he needed to excuse himself from the room a few times. So I'm gonna be evaluating which movies I bring him to in the future more often. I can't just willy-nilly say, he's seen it before, he likes it. Because now he knows. He has a sense of his own mortality, I think. He's starting to develop it.
I love that he kept asking questions.
Yes.
And you kept answering them, because it's like, I've never seen a parent just actually answer them. They just be like, oh, it's just part of the movie, or don't worry about it.
The greatest teaching I will ever do in my life is for my children. And so answering his questions is the most important thing that I can do right now.
And he wouldn't repeat them.
No.
He would be like, oh, well, what is this again? Or what is this
Yeah.
again? It's just, okay.
Yeah. He's a smart kid. He gets top scores in his class, and he's super sharp. I'm really proud of him. Anyways. Okay, what else? Questions? Please come prepared with questions for next week's final exam review. Just like with all of my reviews, it is based entirely upon the questions that you ask. Okay? I do not have a formal sheet of paper that says review this, review this, review this, review this. My test is cumulative. Your review this is the class. Look at the syllabus. That's what you need to review, right? So come with questions based off of, hopefully, how confident you are in your notes. If you feel like your notes are weaker in one place than they are anywhere else, come with questions and ask about those things that you feel like you're weakest on. For my students taking this class online, email me those questions no later than tomorrow night. Hopefully you're watching this in good time. No later than tomorrow night, October the 9th, so that on the 10th, when I come to class and I do that review, I have your questions and I can answer them for you. And then please watch this review video before attempting to take the exam. I will not be answering any questions after the exam is open. If our review goes for the normal hour and a half or so that they have been, then we'll close the review somewhere around 11 o'clock. I'll open the final. You can feel free to stay here in this classroom as long as you want that day to take that exam. If you need a nice, quiet environment with semi-reliable internet, right? If you could go use the LRC if you're not as confident in the internet, or you could be in the hallway. The hallway usually is better internet than my classroom for some reason. I wonder sometimes, because cell phone reception in here is spotty and the internet reception in here is spotty. Sometimes I wonder if they did like a design flaw in the building and somehow this room became a Faraday cage. Like they ran so much copper wiring or piping through the walls of my classroom that's why I've had such bad internet reception in this room for the entire almost 4.5 years I've taught here. So, but yeah, feel free to stay here and take that exam if you'd like. But online students, please make sure you get me those questions in good time or I will not be able to answer them. The exam will close 24 hours after I open it, which will probably be somewhere around 11 o'clock Friday morning. And then after I close it, you won't even be able to see the class. I will hide the class because no other assignments can be turned in at that point. None. Zip. Zilch. Nada. That's it. Cut off. Okay? At that point, I am calculating all of the remaining grades and then adding extra credit onto your lowest exam and then submitting your final grades And I will then open the class again. I will unhide the class so you can see it. But whatever grade you have at that point, that's your grade. You can't email me and say, hey, what can I do? The things you could have done, the time for that is gone. I've already submitted the final grades at that point. Okay? This week, this is the time that you can do what you can do before the deadline. All right? Sound good?
Yeah.
Great. Last chance. Any other questions before we jump into the lecture? Okay. I'll tell you more about the final exam when we do the review in a couple of days. Okay? All right. Let's talk about crustal deformation and mountains. Where's my mouse? There it is. Okay. Do you all remember what forces cause deformation?
Pressure.
Pressure. Excellent. What's the other one?
Environment.
I mean, pressure is part of the environment. Temperature, right. Heat and pressure, okay? Now, as far as pressure goes, let's call that a different word, stress, okay? Let's call it stress for now, all right? When you deform a body of rock, it can happen in a couple of different ways because of a couple of different stressors, okay? This comes down to materials physics, which is kind of a subset of physics. Physics covers a whole lot of things, right? You've got fluid dynamics, you've got materials physics, you've got thermodynamics. There's all sorts of different parts of physics that you could study. Materials physics has a lot to do with the capabilities that a material has of withstanding certain kind of stressors, okay? So if I were to have a stick here and slowly bend it and bend it and bend it, it would be a materials physics experiment to see exactly how much stress that stick can take before it finally snaps. And so I can do that with multiple materials, with lots of materials. I can melt them. I can do all sorts of things. And so this comes down to what characteristics, what properties do my rocks have as a body, as a whole, that the stressors need to surpass before deformation can occur, okay? So if I am pushing, if I'm pulling, if I'm grinding, if I've got shear stress, okay, my rocks are going to react to those inputs at different levels, at different times, based upon what they are, right? We learned this with minerals, we learned this with rocks. Bodies of rock are no different. So deformation is any change that occurs in a body of rock. This includes changes in size, location, orientation, okay? Not so much the content. If we're getting a change in the content of our rock, what does that sound more like? Metamorphism, exactly. Okay, that's metamorphism. We're not talking about metamorphism. We're talking about just the deformation component, the body of rock as a whole. Okay, so let's talk about 3 different kinds of stress that we can see that causes deformation. The first one is compression stress. It's pretty easy to visualize that, right? When you have some flat layers of stuff, like this sheet of paper, flat, right? What happens if I give it compression stress from the sides? Yeah, it bends, it deforms, okay? Now, what would happen if I were to give it tensional stress, pull on it? Yeah, this sort of paper would rip. Perhaps there's a very, very small amount of stretching. But if I have a different material, like this rag, and I give it tensional stress, yeah, this material can stretch a little more, right? Yeah, it's a little more elastic. And so we have bodies of rock that will also stretch. They will deform out, becoming thinner layers as they stretch, okay? Then there's that shear stress we talked about when we learned about faults, this sort of unequal stress. And because we have multiple different types of rock and you've got this unequal stress, that's what eventually causes the faults that occur at these sort of angles. like that, right? We could get a fault forming along there, okay? Shear stress, tensional stress, compressional stress. The three kinds of stress that typically cause deformation in bodies of rock. Now, these bodies of rock, layers of rock, formations, whatever term you want to apply to this, okay, they are going to deform in a couple of different ways. They can react in a couple of different ways. The first one is elastic, okay? Like our good friend, the rubber band. Remember this when we learned about earthquakes? You take that rock and you stretch it 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 until finally what happens? The friction is overcome by the massive quantity of stress. Okay, the friction holding the rubber band in your hand is no longer greater than the amount of elastic energy built up in that rubber band. And so it slips out of your hand and snaps back to its shape. Or the rubber band itself breaks because the material itself cannot withstand that much elastic energy. In either case, you get that release of energy that creates your earthquake, right? So you get that removal of stress, that release of energy like that, very fast, and that causes your materials to break. Or, depending on the material, it could move. Okay, so if an earthquake happens, you could have a permanent movement along the fault line, or that release of energy and stuff kind of snaps back to at least close to where it was before. It kind of depends on a couple of other things. But you get that release of energy that is built up through this elastic response to the buildup of stress. Okay. There are a couple of other ways that this deformation can occur. There are many materials that when they receive this stress, sure, there might be a little bit of flow, there might be a little bit of slippage, there might be a little bit of elasticity, but pretty much everything at some point is going to break. Okay? This is brittle deformation, like this guy's window. Feels like a typical work day to me. Oh, yes. You should see how many windows I go through in my office. No. My office has no windows. That's why. It's because I would break them, yeah. No, that's brittle deformation. You see how that glass, under the impact of that, hey buddy, under the impact of that computer screen, shattered outward into those thousands of little pieces? That's brittle deformation. Okay? And then we've got ductile deformation. D-U-C-T-I-L-E, ductile. Okay? What does that mean? That means that under stress, our material deforms and flows. Okay? It doesn't really break. It maintains the fact that it's a solid. Some materials do this easier than others. Play-Doh, right? Clearly a solid, but capable of taking on multiple shapes. How do you make Play-Doh take on a new shape? You mold it by doing what with your hands? You're applying pressure. If I left Play-Doh sitting right here, just a ball of Play-Doh sitting right there on my desk, at any point will it ever form another shape if I just leave it sitting there? No. It'll get hard and gross and nasty, right? I'll pick it up in a few months and go dong, right? It'll turn hard, right? That's it. However, if I pick it up and I squeeze it and I push it and I shape it and I roll it and I stretch it, I can make whatever shape I want. That's ductile deformation. Okay? Yeah.
He yawned just earlier.
Not surprising. I fed him on Saturday. Gave him a pretty big rat too. He's graduated up. He can eat weaned pups now. Okay. Questions about deformation at all? No? Great. All right. So what's going to contribute to the type of deformation that we see? Obviously, there are a couple of givens. The composition of your rock is a huge factor. Rocks are made out of minerals, right? We've already learned through hard experience in my class, right, that the properties of rocks are very dependent upon the properties of the minerals that make those rocks. Just like the ingredients in a cookie determine what kind of cookie it is, right? If I put oatmeal and raisins and brown sugar and vanilla in my cookie and then handed it to you and said, have a chocolate chip cookie, you'd think I was pulling a cruel joke on you, right? Okay, I need to take a moment for a tangent here. We've all had that moment when we're kids, when we bite into an oatmeal raisin cookie and think that it's a chocolate chip cookie, and then we spit it out and think, oh, that's gross.
And then you eat it.
Y'all are adults now, okay? You're in college, you're adults. It's time for us to finally acknowledge that oatmeal raisin cookies are bomb, okay? Yeah, okay, good. It's time to grow up and admit oatmeal raisin cookies are actually the bomb.
But now with
Not better than chocolate chip.
I'm not saying they're better. I'm just saying
They're tolerable.
forget that moment we all had in our childhood and actually admit the truth here. All right. Okay. Coming back on center. Okay. So whatever your minerals are in your rock determine the properties of your rock. And whatever your rock is made out of determines the property or the manner in which your body of rock itself will deform. Because all of those properties build up, okay? They're all variables in this equation, so to speak. I know you'll shuddered as I mentioned math stuff. Don't worry, there's no math here, okay? So if I have, say, a body of limestone, it will react differently to stressors than granite will. Easy enough. Okay, so some of the stressors, we've got our temperature, right? Increasing heat. Do you think increasing heat or lower heat is going to encourage deformation? Okay, this depends on the deformation in question, right? Let's go back to our example of that chocolate bar. What happens when I put some stress on a frozen chocolate bar? It snaps. What happens when I put stress on a warm chocolate bar? It bends ductily, right? So it's not that deformation can't occur in both high and low. It's just that different deformation will occur, okay? So higher temperatures typically lead to more ductile deformation in chocolate and rock. Imagine that, right? And then there's your pressure. You've got different types of pressure, right? You've got your confining pressure, but you also have your differential stress. That differential stress can take the form of compression, tensional, or shear stress. These are all factors building into it. Plus, the amount of time will determine, that's exposure. Time is the amount of exposure over time, I guess you could say, to these stressors, right? So if I experience a few days of this stress versus a few centuries of this stress, I'm going to have more deformation, right? So let's talk about some very interesting deformation that can occur, just as an example. Halite. Remind me what the mineral halite is.
crystal, like salty.
It is the salt crystals, exactly. It is the mineral halite is salt. Okay, we're all familiar with that now. Excellent, fantastic. How does it form? Usually through processes of evaporation or hypersalinity, okay? So let me tell you a story. Millions of years ago, during a time called the Jurassic, okay? Dinosaurs roaming the earth, but we're not worrying about the dinosaurs, right? We're talking about out in where the Gulf of Mexico is now, there was a shallow sea. Call it the proto-Gulf of Mexico, if you will, okay? There was a shallow sea. And at different points during geologic time, it actually, a land bridge formed during, perhaps it was during the late Jurassic or to mid to late Jurassic, okay? Some land bridges formed, some uplift occurred, and that shallow sea got cut off from the rest of the ocean. Now, what happens when a body of water, a salty body of water, gets cut off from the rest of the ocean? Evaporation is occurring. And as evaporation occurs, the salt can't leave with the water, and your body of water becomes hypersaline. Y'all familiar with the Dead Sea out in the Middle East? The Dead Sea, you ever heard of the Dead Sea? Okay, the Dead Sea is the saltiest body of water on the planet. It is so salty that if you go and you walk on the beach, you're crunching on salt crystals. There is salt everywhere along the coast of the Dead Sea. We call it the Dead Sea because nothing can live in it. It is too salty. Okay? So, imagine something like that happening to this huge area, about the size of the Gulf of Mexico, perhaps a little bit smaller at this point. Okay? And so the water is evaporating away, leaving behind thick layers of salt and gypsum. Okay? These evaporite minerals that you learned about when we discussed sedimentary rocks. And then water starts coming back in. Perhaps that land bridge gets weathered away. Perhaps it is no longer being uplifted. Whatever the case may be, it gets removed. Water can start entering back in. What does it bring with it? Sediment. That sediment covers your deposits of salt and gypsum. And so you get layers of salt and gypsum that have been covered by layers of sediment, which gradually do turn into sedimentary rock. Now, if prior to the deposition of that evaporate mineral, the salt, there was some, or not prior, sorry, after the deposition of that salt, when the sediment was being deposited on top of the salt, there was some thick layers of organic matter deposited. Say that there was lots of algae or lots of foraminiferans or whatever the case may be, and all those little organic bodies and their organic contents got preserved in the rock. That's going to gradually become oil, right? Hydrocarbons are going to result from this. Now, I told you that hydrocarbons like to hang out in highly porous rock. Remember that? Remember porosity and permeability when we talked about that? Well, what happens to the salt under stress? Salt is extremely ductile. Okay? That means that it doesn't take that much pressure, and salt will start to deform kind of like that Play-Doh will. So if I have my layer of salt down here, and there's some shale above that, and sandstone above that, and limestone above that, and then we're back to shale, and that's the surface right there. What's going to happen is this salt under so much pressure from being buried that deep, it's going to try and find any way up to lower pressure zones that it can find. So if there's a fault or a crack or whatever weakness in this layer of shale up here, it's going to ductily flow up through that. And as it flows up through it, it's going to widen it. It's going to scrape stuff off the side and widen it more and more and more. And then it's going to do the same thing through this layer of sandstone. Shale and sandstone are relatively brittle. And so they're going to crack and they're going to break and they're going to deform out of the way, kind of allow the passage of the salt through it. Until finally the salt encounters a material that also deforms ductily. Perhaps a limestone, for example. Okay, so the limestone, or whatever this layer up here is, deforms above it, making a sort of cap. It pushes upwards, not allowing the salt to go through it. And so you get this sort of plume underneath of it. We call that a salt dome. You ever heard of that term before? Petroleum engineer, you're going to know this term very well. Okay? Because it is around these salt domes that we will often find oil. Why? Oil is a fluid. It is a liquid. It also is trying to get to zones of lower pressure. If my oil is hanging out in this porous sandstone, it can't go through this rock, but it is still under enough pressure that it would like to. Then when this salt dome pushes up to lower or lower depths, it's pushing up to lower depths. You know what I mean, right? And it's causing the sandstone to kind of make this sort of bowed upward shape. Then my oil is going to flow through the sandstone and collect in a ring around the top of my salt dome. There are hundreds of these salt domes in the Gulf of Mexico because of those layers of salt that were deposited in the Jurassic. That's why we have so many oil rigs in the Gulf of Mexico. Because of this. It's cool, huh? If any of you ever go to Louisiana, how many of you like Tabasco? I like Tabasco. I like putting Tabasco on eggs. It's delicious. Okay. Huh?
Chulu's better.
Cholula's better. How many flavors does Cholula have? I think they have maybe 1 or 2. There are like 26 Tabasco flavors. I like Tabasco a lot. But the Tabasco factory is in Louisiana, right there next to the Gulf of Mexico. And they built the factory on top of what is called Avery Island. But Avery Island, if you look at it on a map, it's a roughly circular island, okay? And the reason why they built that there is because it's a salt dome. You only have to drill maybe a couple dozen feet under the rock, and there's the salt dome. Now, why did they put the Tabasco factory there? Because it takes so much salt to make Tabasco. They put some in the Tabasco for sure, but part of their process is they put the chilies and the vinegar and the salt in these casks, these oak casks, and they seal them tight. And then they pack these suckers all around with salt. They use so much salt. And why is it there? It's to keep moisture out, right? You pack something with salt around it, no water is going to get through to it. It's just not gonna, okay? And they leave it there for about 5 years. Each cask of Tabasco is like fermented for about 5 years or something like that. And then they remove all the salt and they take the cask out and open it, and then they go through the process of straining and all of that before they bottle it up and sell it. But they go through so much salt in this map, Gulf of Mexico. Let's just look at images. Yeah, here we go. Each one of those blobs is a salt dome. That's a depth map of the Gulf of Mexico. Yeah. And around each one of those have people been exploring or are still exploring for oil. So,
A lot of oil.
yeah, Gulf of Mexico has a lot of oil in it, which is why whenever there's a leak, like, y'all ever seen Deepwater Horizon? It's a really good movie. It's got Marky Mark in it. He doesn't go by Marky Mark anymore, but I still call him Marky Mark. You know who I'm talking about?
My mom really likes
Mark Wahlberg. He used to be a rapper. We called him Marky Mark. Yeah. Okay. So, actually, if you go down Farm to Market 1053, it's a road about an hour and a half down the road, okay? You're going to eventually, I usually drive down that on my way to Big Bend. I kind of go out of my way just a little bit to go down 1053 so I can look at this. But you're going to notice that the road, the 1053, deviates a little to the left, kind of goes down into a hole for a minute, and then comes back out. And there's a big old like basin sort of hole off to the right. That's where a salt dome used to be. And this is where drilling for oil off of salt domes gets really tricky, okay? Because if you're not careful, you might accidentally introduce water to your salt dome. What does water do to salt? It dissolves it. If you accidentally introduce a source of water to your salt dome, all of a sudden the salt starts dissolving, getting carried away by the water, and you're left with a big empty space underground. And what does the ground above it do? Collapses down into it. And so this big divot off to the side of the 1053 is where they made a mistake. They were drilling for oil off of this. They accidentally introduced water. There's water is a big part of the drilling process. They accidentally introduced water to it, and it started dissolving it. And the entire, like the drilling structure and everything kind of collapsed into it. And more top surface of the ground is collapsing down into it. And they have to keep moving the 1053 further and further away so that it can stay out of the hole. So that's case in point why you got to be careful when you're drilling around a salt dome. Okay. Folds. We've learned about folding before when we discussed metamorphic rocks. Well, now let's talk about some of the terminology for a fold. A fold is another example of deformation. Stuff goes up, stuff goes down. What sort of stress makes this? Do you think it would be compressional, tensional, or shear?
Equal.
It can't be equal, or else we wouldn't have deformation, right?
Compressional.
Compressional stress is going to make your folds. Yes, the pushing stress that makes things kind of make those wave shapes. These are those wave shapes. When you have this shape, your up shape, so to speak, let's call it a convex fold, okay? We call that an anticline. These are anticlines. Whew, that marker is smelling strong today. If I collapse or I start talking about purple elephants, take the marker away from me, okay? These down folds or concave folds, we call those synclines, okay? Anticline, syncline. And it's fairly common to find them paired with each other, right? If I were to take this paper again and bend it, I have an anticline and a syncline here. Whoa, yeah, right? Crazy. Now, anticline, syncline, but there's also one more component here. Plunge. You can tell me this is an anticline. You can tell me this is a syncline. But the other thing that I'm going to teach you that you need to know how to describe these things is plunge. That is, it's very rare to find one of these that is it's just sitting on the surface, just perfectly level. Layers of rock are rarely that perfectly level. Normally, right, they're tilted to some extent because tectonics happens. I need to make bumper stickers, right? Tectonics happens. So many people would get it, right? But the same is true of these anticlines and synclines. They're going to do this. They're going to do that. They're going to be rolled. They're going to go that way. It's going to be this. It's going to be that. So you're going to be all over the place, right? Plunge is a way that we describe these things where if it is if it's tilted to some degree, then, and this is my ground level, right? It's going to be, this feature is going to be rounded off in the direction that it is going into the ground, that it is plunging into the ground. That's what we call plunge. Take a look at this right here. This is either an anticline or a syncline. I'll get to that in a minute, okay? But notice how all of the layers are rounded off on this end, right? It is plunging that way. It is slightly angled. What was originally a flat plane of rock got folded and then tilted. So now that rounded off edge where the layers are going back in the ground is right there. Okay? You following me? That's what plunge. So I would say this is an anticline plunging 86 degrees to the whatever. Okay? Just using compass coordinates. Okay? 86 degrees. Let's see, northeast. Actually, that would be pretty much east. East, northeast. Okay? Northwest. Yeah. Southwest.
But that right there is an example of the
Yeah.
village part.
This is plunging.
Oh.
I would describe this as plunging to whatever, direction that is. But now let's talk about, is this an anticline or a syncline? How could I tell? Can you tell me if it is folded up and we have simply lost, like all of the layers up there have been weathered away, leaving only the ground level exposure, or if it's folded down and we're seeing the tops and it's really, each layer is kind of packed in a cup shape? How can you tell? It can't be both at the same time. No, because it's either going to be this or that, right?
Is it two different deformation structures?
Nope. This is either an anticline or a syncline. How? How do you know that?
that thing is going up, but the front is going down. So that's why it's making, you know.
Can it be an anticline and a plunge at the same time?
No, it can't be both an anticline and a syncline. That's one feature.
No, anticline and a plunge. Or
Oh,
you
it
have a
can be,
plunge.
but I'm not talking about the plunge. We already discussed the plunge. I want to know if you can figure out how this could be an anticline or a syncline. Tell me how it could be one of, like, which, how do we tell?
Well, if we're identifying the fold as a plunge, then we must be talking about the one on top, and that one has an arch.
But remember, plunge has nothing to do with this.
Oh,
But, so you're telling me, is it an anticline or is it a syncline? How could we tell? Any
it has
guesses?
an arch.
Let's see, I need red, green, and let's go with purple. Okay, let's figure it out. If I have 3 distinct layers of rock, purple, red, and green. And then they get compressional stress. They are going to either make an anticline or a syncline, right? In an anticline, I'm going to have I'm just going to leave the caps off of these just for ease. Let's see if I can figure out a way to. I know, and I've got 3 of them out at the same time now. This is dangerous. Okay. That was interesting. Okay. So I've got that. Now I've got red and purple. In a syncline, I'm going to have green and, oh, I did that the other way. Green and red and purple. So now, in that context, do you understand how I could tell?
It's a syncline.
But tell me how I could tell.
The different layers of the rock.
Tell me more about the layers of the rock.
The small, the one on the up is the least, has the least mode.
The least what?
The least, like the green, which will be like the brown here, is the most. It has the most. You know, it covers more.
My actions is the story.
Yeah.
That's not really it, because that could have more to do with the thickness of each layer, not so much anything else. Someone remind me of the law of superposition.
The deeper, the older.
The deeper it is, are you sure you don't want to be a geology major? Okay, the deeper the rock is, the older it is. Law of superposition. Oldest on bottom, youngest on top. In an anticline, so here, is green older or younger? Oldest. Then that's older and that's youngest, right? So in an anticline, what's going to be my top layer? The youngest. And the bottom ones? The oldest. In a syncline, what's going to be in the middle? No, what's in the middle?
Oh, the youngest.
The youngest. So if I were to weather both of these features down, let's say ground level is now, let's get a different color for this. Ground level is now here. This is what I see exposed, right? from the top-down view, like what we're looking at here, in an anticline, I'm going to see oldest in the middle and youngest. Oh, yeah, because purple is the youngest. And youngest on the outside, right? With our middle one between the two. That's what I'm going to see from the top down, right? Whereas with a syncline, I'm going to see youngest in the middle, and then the middle one, and then oldest on the outside. So how could I tell if I'm looking at an anticline or a syncline?
If the one in the middle is the youngest.
Is my oldest in the middle or the outside? Is my youngest rock in the middle or the outside? That's how you can tell. Otherwise, they look pretty much the same if you have no context. Figure out the ages of the rock. Then you'll know. Cool? Now, if we're looking at this less of a linear feature like a fold, which can go for some distance, the same principle can be true for local, like sort of less linear features, okay? So if I have some uplift, local uplift, say because of a magma chamber rising to the surface, and it's kind of causing the rock layers on each side to be uplifted like this, okay? Then you're going to end up with a sort of what we call a dome. So if I were to take, if this represents the land, right? And then my magma chamber rises up in the middle like that. That's my dome sort of shape, okay? And then it gets weathered down. So you're looking at it in cross section. We're going to have oldest in the middle and youngest on the outside. Okay? Because each successive layer of sedimentary rock that's deposited on top of this is deposited on top of that dome. And so if I weather it down to a cross section, you're going to have oldest in the middle and youngest on the outside. Very similar to an anticline. Okay? Whereas with a basin is kind of a low point, a low area. The oceans reside in basins. That's why they're full of water, right? Lakes often occupy basins. Bays, rivers, right? All of these can occupy a basin of some kind. Deposition occurs in a basin. So if this is greatly exaggerated, by the way, if this is my basin, let's say I've taken my entire basin and I kind of squeezed it. This is a 100 miles basin. It's not that steep, right? And then I get some deposition. My first layer of deposited rock. My second layer of deposited rock. And my third layer of deposited rock. My basin is gradually getting more and more filled in. Okay? And then after it's completely filled in and some time passes, it gets weathered down. Looking at the surface view, you're going to have youngest in the middle and oldest on the outside, like in a syncline. Right? Youngest in the middle and oldest on the outside. This is Michigan, by the way. This is the entire state of Michigan is basically one big basin that got filled in. Okay? Gradually getting older the further out you go. Yeah. Yes. We live in what we call the Permian Basin. This was a shallow sea that got filled in with sediment. Okay? This is what it looks like geologically. Very similar to this. Okay? Questions about any of that? Great. Right. Quick recap on faults. We've got your reverse fault, we've got your normal fault, and your strike slip fault. We talked about all of those things, okay? Most of these occur within the top 15 kilometers of the crust. Someone tell me why that would be the case. Why do these faults typically only occur, and some do go deeper than that, but typically they will only occur in the top 15 kilometers of the crust? Why? Why would faults occur typically only in the top 15 kilometers of the crust? Someone remind me what a fault is. Perhaps we should start there. Bingo! It is a crack in the crust. What kind of deformation is that? Of the three types that we just talked about not long ago.
Shear.
No, that's a type of stress. What type of deformation? Say it louder. It's brittle deformation. Good. It's brittle deformation. For things to deform brittly instead of, say, ductily, what sort of conditions do we need? If we ignore materials for now,
Temperature.
what about temperature?
High or low temperature.
Well, which one is it?
Oh, it's brittle. It's gotta be low, right?
Uh-huh, yeah. Things tend to behave more ductily under higher temperatures. Therefore, for something to deform brittly, like making a crack in the rock, you would need relatively lower temperatures. Why would that mean most faults typically occur in the top 15 kilometers of the crust? It's colder at the top, hotter at the bottom. Because of what?
Climate.
Hmm?
Climate.
Not because of the climate. What's going on the deeper you go?
The core.
The heat is increasing. What do we call that?
Convection.
Huh?
Convection.
No, convection is a process that is happening kind of consecutively with this, but not the same.
I think it's like metabolic, but
I'll give you the first word. Geothermal.
Geothermal energy.
It's the geothermal gradient. There we go. The geothermal gradient is the rate at which heat increases the deeper you go underground, right? Therefore, faults occur in the top 15 kilometers typically of the crust because above that point, the crust is still cool enough, the geothermal gradient has not increased enough that our material behaves semi-ductily. So above about the 15-kilometer point, the crust will behave more brittly. Therefore, it will crack. Therefore, we make our faults. Did you follow that logic? Did that make sense to everyone? Should I explain it differently or are we good? Great. Okay. Well, I'm going to introduce you to one more type of fault. Okay. The thrust fault. You learned about strike slip faults that have shear stress and go like this, right? They scrape along each other like so. You learned about reverse faults right here, okay? Where your hanging wall is moving up relative to your foot wall. By the way, when that happens, you'll typically have an upland or a mountain range of some kind on your hanging wall. Why? Because it's an increased elevation above your foot wall zone. Then you have a normal fault where the hanging wall is moving down relative to your foot wall. And so you're going to have more mountainy sort of terrain on your foot wall. Okay? Normal faults are the result of tensional stress. They are moving away from each other because there is tensional stress pulling those two sections apart. That's why that fault formed in the first place. Then you have reverse faults, where they are pushing towards each other. One is overriding on top of the other one because of compressional stress, right? Well, in a thrust fault, it's very similar to a reverse fault. Compressional stress, again, with a small difference. Notice that in a reverse fault, it slices through, our fault plane slices through all these layers of rock. So that layer right there is present up there because the the hanging wall is moving up, right? In a thrust fault, you still have that compression stress, but instead of slicing right through those layers of rock, our fault plane formed between layers of rock. Right there, say between that sandstone and that shale. And so it tends to be a much lower angle. If that's somewhere like 70, 75 degree angle, this is more like a 15 to 20 degree angle. Right, much lower. Now, what does that mean?
A lot more movement on the top, on the hanging wall.
Huh?
Is there a lot more like, I guess, movement on the hanging wall? On the surface above the hanging wall?
For which fault?
For the thrust fault.
For the thrust fault, you're saying there's more movement here? Why is there more movement?
Because it has a lower angle.
Lower angle, therefore, what does that mean? Why would a lower angle mean?
Faster?
Huh?
Does it move a lot faster?
It might not move faster. Maybe it does. It doesn't have to do with the angle of repose, but why does the angle of repose matter?
Gravity.
If I have a 75-degree fault, all that rock has to fight gravity at a 75-degree angle to get shoved up. If I have to fight gravity at a 15-degree angle, much less of a fight, right? Right? Is it easier to push a car with a broken down engine up a 75-degree slope or up a 15-degree slope? Yeah, right? So, yes, our thrust faults often are a lot of rock that moves a very far distance. There have been a lot of orogenies, and you will learn about these. Those are mountain building events. We'll talk about those in a moment. That occurred that made our Rocky Mountain areas, the Laramide orogeny, and so many others, Nevadan. Okay, there are so many orogenies that included thrust faulting that went all the way from the West Coast and shoved material into the middle of North America, like to make our Rocky Mountains. That material can go a very far distance because thrust faults are much lower angle and can shove a lot further. Okay, that is a thrust fault. All right. Now, like I just said, a mountain building event, we call that an orogeny. An orogeny is the event. Orogenesis is the act of mountain building. Orogenesis is the act of mountain building. Okay? This is folding and thrusting and any other deformation that is necessary to create an area that is uplifted above the rest of the surrounding area around it. Okay, we're gonna have some special guests. My parents just walked into the hallway. They'll join us in here. They're visiting from North Idaho. Yeah, they live in the mountains, so very appropriate lecture for them to come visit on. So, erase all that. Let's talk about a couple of the different ways that we can have mountain building. Okay, huh? Oh, he's not talking to me. All right. You can have the subduction of one plate under another. We've learned about this. What do we call that? What kind of boundary is it? Convergent plate boundary. Now, what happens if two oceanic plates run into each other? You remember this conversation? Well, we'll get there in a second. When two plates run into each other, what has to happen? One will go down or they will crunch together and make a big mountain range. In the case of two oceanic plates, One will subduct under the other. Which one is it? You remember this?
Is the one
The
that-
oldest one. Good. Why the oldest one? It's thicker, it's colder, and therefore denser. Okay? So the denser one will subduct underneath of the youngest one. Yes, of course. Okay? And what's happening here? Why are we forming magma down here between the two plates, the overriding and the subducting plate?
Does it get pushed into the Earth's core?
It's not going anywhere near the core. It doesn't make it out of the upper mantle, right? But this is getting shoved down. Heat is increasing. But what is this plate taking down in there with it? Huh? Water. And what does water do to the melting point of rock? It what? It lowers it. Water lowers the melting point of rock. And so as this thicker, denser oceanic plate is subducting underneath of the overriding plate, taking all that water down there with it, because that's hundreds of feet of rock that has soaked up water for all that time. That water gets turned into superheated, and that superheated water wants to escape back up to the surface because it's got lower pressure. And as that's making its way up into the mantle and the lower crust, it's lowering the melting point of the rock. The geothermal gradient and the melting point of that peridotite mantle can cross each other. Boom, bada boom. You got pools of melted magma, which we call magma chambers or mantle plumes, right? And those rise up to the surface, and that's what makes our volcanic island arcs. That's how you make your Japan and your Philippines. And all of those big island arcs that we have out in the Pacific and around the world are made through this process. That's the first way we can form these mountains. Now, what happens if we have the same interaction, except instead of two ocean plates, we have a continental and an ocean plate? Which one's going to subduct? The ocean plate, because it's denser, right? Even though it's thinner, it's denser. And so the ocean plate subducts underneath of the continental plate. The same process occurs. The dewatering of your ocean plate introduces water to your mantle, which is already hot enough to melt, but can't. Until that water is introduced and it lowers the melting point, they cross each other, you get mantle plumes that come up, and you get your coastal mountain ranges. This is how you get your Cascades and your Andes and all of those, okay? That's your second way of making mountain ranges. Then we have accretionary belts. Now, an accretionary belt is kind of a combination of the first two. What happens if my volcanic island arc that we learned about in the first example crosses the plate? It gets shoved all the way across the plate through as the plate is moving, as new material is made, and that island arc gets pushed gradually all the way to the other side of the plate. And then it interacts with the second example, where that ocean plate is subducting underneath your continental plate. Your volcanic island arc can't get pushed down through that boundary. And so instead, it gets scraped up on the side, okay? And this gets scraped up, and it's left there as the rest of the plate underneath of it keeps getting shoved down, okay? This is called an accretionary belt. And this is most of the state of California, which is why California has so many geologists. The quantity of geologists that live and work in California is leaps and bounds above pretty much anywhere else in the United States, because pretty much the entire state of California is dozens of island arcs that have gotten shoved and scraped onto the side of North America as all these plates got pushed underneath of North America by the Pacific plate. Okay? So trying to untangle that mess, California is a mess in more ways than one, okay? This is just one way, right? Geologically, it's a mess in pretty much every other way possible.
Thanks.
Yeah. Okay. Then finally, collision belts. Now, a collision belt is what happens when two continental plates run into each other. What happens then? Is one less dense than the other? Not really. They're both really thick. They're both made out of that less dense material, mostly felsic and intermediate material, right? So instead of subduction, what happens?
Convert.
Well, it is a convergent boundary. You're right.
They go up.
Yeah, they go up. The two plates collide with each other, and because they're both equally dense, neither one can subduct under the other. They crunch together, and you make this massive metamorphic zone that makes an incredibly tall mountain range that we call the Himalayas. Right? Yeah, the tallest mountain range in the world right now, the Himalayan mountain range. You can look at that map right there. That huge Himalayan plateau happened when the Indian subcontinent collided with Eurasia, right? And mostly in the last 55 million years or so is when that mountain range really kind of picked up. And it is still growing because the convection cell underneath of the Indian subcontinent is still shoving it up that way. So there is some growth that is still going on. It's really interesting because something you'll learn about next semester in 1404, I'll show you, is that Australia is actually also connected to the same convection cell. And so you can kind of see how Australia and India, their progression upwards, they match each other, and then India runs into Eurasia. And you can see in the record how Australia kind of was like, whoa, it got body checked a little bit and started twisting a little bit towards Eurasia. And now the projections of the way that Australia is traveling, eventually it is going to squish New Guinea and Micronesia and Polynesia. It's going to sweep all of those up, and eventually it's going to crash into Southeast Asia in its current projection because it got that sort of change of angle when India ran into Eurasia. Okay, we'll talk about that more in 1404 next semester. All right, and then the last thing I want to mention isn't so much a way that you make a mountain range as much as it is how a mountain range can continue to push up even if it's not actively growing. This is called isostatic adjustment. We learned about this when we talked about glaciers. Do any of you remember what isostasy was? Remember I told you about that mile-thick glacier that sat on top of North America during that big ice age we had? What did it do to the crust? It scraped a bunch of material off, it's true, but as it was sitting there for thousands of years, all that ice, those so many tons of ice in that mile-thick glacier, what did it do to the crust? It pushed it down. Yeah, it shoved it a little bit into the mantle, not much, but enough to make a depression. And now that the ice is gone, what fills that depression? Water. And we call that water the Great Lakes. Okay? The Great Lakes pretty much exist because of all that material that was scraped away, but also the fact that the crust got shoved down into the mantle. However, isostatic adjustment is happening. That's the rebound effect of the crust. The ice melted less than the blink of an eye, geologically speaking, right? It was here, it was gone. It did its thing, and now it's gone. And now the rock is slowly pushing back upwards, which is why the Great Lakes are expanding outwards. They're getting shallower, but also expanding outwards as all that water needs to go somewhere. Remember I told you how Chicago is eventually going to get flooded out? Big loss, right? Okay, so it's going to get flooded out, and all those other communities, it's going to be something that people are going to have to adapt to. In a couple hundred years, that water is going to continually move and encroach on those civilizations, or those communities, especially as you also add in the fact that sea level is rising as warming trends continue. So you're going to have the isostatic adjustment, but also more water coming into the system from the ocean as the oceans rise, right? Global water levels are going to rise. So how does this relate to mountains? Well, imagine how much a mountain weighs. That's an incredible mass of rock, right? And so not only does it push up into the sky, but it also goes deep into the ground. The roots of the Himalayas go extraordinarily deep. They push down into the mantle. That mountain building didn't only happen where we can see it. It happens underground too. That intense metamorphism. And so as weathering and erosion is happening on the top of our mountain range, carrying material away, that weight is removed, the bottom of our mountain range is getting adjusted upward because of the same isostasy. Okay? It's getting slowly pushed upwards. And so while our mountain may no longer being actively built, right? The collision energy may be all expended, it is still going to get shoved up a little bit as the crust is adjusting for the mass being removed above it. Which is why in the older mountain ranges, like the Appalachians, they're usually deep crustal metamorphic rock, as opposed to the more recent mountain range sort of material, which is essentially, think of the Alps, which is essentially ocean bed from when that used to be the bottom of an ocean not that long ago. Instead, an ancient mountain range like the Appalachians is made out of deep crustal metamorphic rock because it's essentially the roots, the base of that mountain range that used to be deep underground and now has been isostatically brought to the surface. Any questions about that? Any questions about anything we talked about today? No? Well then, my friends, that's all I've got for you. That is the end of Geology 1403. We have our final exam review. Oh, thank you. Yes, applause is now appropriate. Thank you. Thank you. I appreciate that. I'm so happy I'm done. You're not done yet. You have the final still. So next time, Thursday, we'll be here. We'll start normal time. We'll go as long as the questions go. And once the questions dry up, I'll open the exam. Deal?
Yeah.
Okay. Well, then you can use the rest of we've got about another hour and a half for today. You can use the rest of that time to retry labs. You can do discussion boards. You can work on your notes. You can prepare a list of questions for Thursday. However you want to use your time, please feel free. So for those of you that are watching this online later, please make sure you get your questions for the exam review to me no later than tomorrow, Wednesday night. That's the 9th. Okay, that is October 9th, no later than tomorrow night, so that on Thursday, I have those questions to come into the review with. All righty, I'm going to end the recording here, and y'all can move into doing whatever you feel like your time is best spent doing.